Okay, in this video we're going to begin the introduction of an important mathematical structure called sets. You've probably worked with sets before. You may have seen some of the familiar symbols and operators with sets, but we're going to review this just to make sure we're all speaking the same language and have the same level of understanding. You may see a few things that you haven't seen before, but let's go ahead and get started. The basic definition of a set is that it's just a collection of objects. We generally refer to them as elements in a more technical term. And the important thing to understand is the order doesn't matter. One of the other things we want to understand is that when we write a set, we use a set of curly braces, and we put elements of the set separated by commas. Right? The fact that the order doesn't matter means that the set A, B, C is the same as the set C, B, A. And there's a definition of what it means for two sets to be equal. They have to have the same elements. We don't repeat elements in a set, and we don't worry about the order of the elements in a set. We're just saying these objects belong to this set. It doesn't matter if the element shows up 2 times, 3 times, or 1 time. It's still in the set. There's a few symbols we're going to introduce. We want to have ways of referring to sets. We usually use uppercase letters to refer to sets. And we have this symbol right here that sort of looks like the Greek letter epsilon. And it's used to represent the element of symbol. So we would read this as A is an element of S. And that means that A is one of the elements in the set S. There's also the negated version of the element symbol to say that A is not one of the elements of S. So here's an example of a set we might refer to. Here's the set uppercase R. We generally use uppercase letters for sets, and sometimes we use a meaningful letter if the set has some sort of description that can be used or given. We usually use A, B, and C or S for arbitrary sets. This set R is red, orange, yellow, green, blue, indigo, and violet. These are the colors of the rainbow. And you might see some simple questions in the homework that say, decide the appropriate symbol to put in between these. Now, the important thing to understand with the element and not element of symbol is the element of the value on the left is always an element, a single element of a set, and the value on the right, the argument on the right, is always a set. So we have yellow as an element compared to the set R. We can understand and see that yellow is in fact an element of R. Brown, on the other hand, is not an element of R, so we would fill this in with the slash. Sometimes we want to represent sets that are large, and we don't want to write all the elements out, so we establish a pattern, like in this case 3, 6, 9. We're talking about the positive multiples of 3 up to 99. So we use this dot, dot, dot here to say continue on in this pattern. Now you always have to be a little bit careful that you establish the pattern before you put the dot, dot, dot. 3, comma, dot, 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 99 would not be sufficient. But in this case, you can see that 8 is not going to be an element of A because 8 is not a multiple of 3, and we've already passed the number 8 without encountering it. Now the question really is 84 going to be in this set? One option would be to write all of the elements out. The other option is to recognize that A represents all of the multiples of 3 up to 99. So the real question is, what's 84 divided by 3? Is it an integer? Well, if you remember rules of divisibility, if you add the digits 8 and 4 together, you get 12. 12 divided by 3 is an integer, or you just simply get your calculator out and you see that the answer is 28. So that would mean, as I was just about to say, it is an element, but I wrote not an element. We'd say that 84 is in fact an element of A. Okay, don't worry too much about how neat these symbols look. It's really just a question of, is there a slash through it or not? Okay? So we want to understand, once we have sets and elements, how we can describe whether or not an element belongs to a set or doesn't. We have some different notations too. One way to write a set out is to list all of the elements of the set, and we usually refer to this as the roster method. Right? You just simply list a roster of all the elements in the set. Another more compact and mathematical way that you might see is what we call set builder notation. So in this case, we could describe the same exact set R here by saying let R be the set of all x's such that, this vertical line here means such that, x is a color in the rainbow. Okay? So this gives a rule to generate all the x's that belong to R without actually writing them out. So here's an example of something you might see and be asked to do. A is the set of all x's such that x is a positive multiple of 4 less than 30. So now they want us to write the set out. So now we need to understand what the set builder notation means. Positive means non-zero, right, or non-negative, right? But 0 is not a positive number. 0 is a multiple of 4, however. But because we're saying positive multiples of 4, we're going to start with 4, and then 8, and then 12, and then 16, and then 20, and then 24, and then 28, and then we stop. Okay? So if you're given this set builder notation, you should be able to write the elements of the set out, which will help you sort of understand what this set builder notation means. Okay? Moving along, there are a few common sets that we'll refer to throughout the semester if you haven't seen them already. There are certain sets like the natural numbers. Natural numbers start at 0. There's a similar set called the counting numbers, which starts at 1. But the natural numbers is usually designated by the boldface uppercase N. Integers are something we work a lot with in discrete math. Integers include positive whole numbers, negative whole numbers, and 0. They're generally referred to by the boldface capital letter Z. The rationals are referred to by the letter Q. Rationals are all the P over Q. We did this back in chapter 1 with our proof that the square root of 2 is irrational. P over Q, where P is an integer, Q is an integer, Q can't be 0, and P over Q is in lowest terms. So we refer to these as the rationals, and the reason we don't use the letter R for rationals is because the letter R is designated for the real numbers. Okay? So there's not much here you really need to memorize at this point, but we certainly will refer to Z, Q, and R later, and you should probably familiarize yourself with those. Okay. Now most universes we operate in math have the concept of nothing. Usually in numbers we represent that with 0, but for sets we have a special set called the empty set. And the empty set can be written most directly as a set with literally nothing inside of it, just an open and closed parentheses and no elements. And that demonstrates the fact that there is, in fact, nothing in this set. Usually, mathematically, we use this circle with a line through it, the null symbol. That's probably how you'll see it in most math books. But if it's easier for you to understand that it's empty and reinforce that idea, you can certainly use the empty braces. Okay? So here's a couple of examples. The set A of all x's such that x is a month of the year beginning with Q. If you had to list out all of those months, there are no months that begin with Q, so you would use the empty set symbol. Again, you can use the open braces. It doesn't really matter. This is what you're probably more likely to see in the text. Another example that shows us a use of the empty set, where x is all the positive multiples of 7 that are less than 5. Right? Well, the first positive multiple of 7 is 7, so there are none, so we would represent the set B as the empty set. Okay? Last thing we're going to talk about here is the cardinality of a set. The cardinality of a set is the number of distinct elements in the set, and we designate that usually with the absolute value lines around a set. So for example, the set R, which we used before to refer to the colors of the rainbow, right? The cardinality of R is 7. A set like this, even though we don't have all the elements listed, 1, 2, 3, 100, right? You can see here that the cardinality of that set, if you counted them all up, would be 100. Now, another thing to understand is if you had the cardinality of the empty set, that would be, in fact, 0. Okay? So that's sort of where the idea of 0 gets tied into the empty set. The empty set is not 0, but the number of elements in the empty set is 0. Okay? Now here's a slightly more complicated example. We have a pattern here. We're doing the multiples of 2, but we're starting at 6. And the question is, how do we find the cardinality of B? Now in a case like this, it's not going to be practical to write all the elements out and count them up. However, it might be easier to think about a set like this, 2, 4, 6, 8, 10, all the way up to 200, right? And think about the cardinality of that set. Well, if we counted from 1 to 200, we would have 200 elements. If we count by multiples of 2, we're basically dividing that set in half. Half we want to keep and half we don't. Hopefully you can see that the number of elements in that set would be 100. Right? Every other number is being crossed out. If we were counting by multiples of 4, we would divide by 4 because we want to count only one of every 4. Okay? So this is going to help us get to the original question, because if you take a look at the new set we have, we've really just thrown in 2 extra elements to it. If you remove those 2 elements from that set, the set originally had 100 elements in it, and you remove 2 of them, you should have 98. Now sometimes people like to do the subtraction of 200 minus 6 and say, well, that's 194, and divide that by 2, and you get 97, and then you have to remember to add 1 because you're counting one of the endpoints. I think that gets a little bit confusing. So I prefer to just think of a big set that either includes this or almost includes this, that's easy to count, and then just sort of tweak the answer based on whether I have to remove elements or throw elements in. Okay. This is another example of a complicated set. I have sets within sets, okay, but I want to know the cardinality of C. If I were to list the elements of C, right, the first element of C is clearly just the element A. The second element of C is in fact a set. So you can have sets within sets, right? But when you're asked for the cardinality of a set, you really want to look on the outermost level, right? On the outermost level, we separate sets by commas. So I really only see 2 commas here on the outermost level. This comma right here is inside one of the other elements, so we're not going to count that one. We're just going to count these first 2. Right? I see the element A, I see the set A here, and I see this other set. It doesn't matter that this last set has elements within itself. The cardinality of C should just be 3. Okay? So you're looking on the outermost level, how many elements are there, even if those elements are sets that have their own elements. Okay? Now that we've established what sets are and some of the notations used with them, we're going to take a look next at subsets, and then eventually we'll get into operations that involve 2 sets like unions and intersections or set difference.